The exponential function is a function defined in terms of calculus. I want to find a function whose slope is its height at every point. And we'll start at height 1. This is the definition of the exponential function. The slope of a function is integral to its definition, so without calculus you can't make sense of it. Let me plot what we're talking about. We're going to start by plotting a point, but then using calculus, it's going to be a little line segment whose slope is 1. To get a new point, I'll just follow the line segment and then glue in a new line segment. Our goal is to continue this process until we've reached 1. We'll see why. By taking tiny steps, we're approximating the true slope because h is close to 0. As we drive h to 0, we get to the exponential function. All we'll be doing is approximating it with tiny steps. So let's start. Here's my starting configuration, and I'm going to use a horizontal offset of 1/4. So it'll take 4 steps to get to 1. Plot unit height, slope, unit slope, which is the exponential of 0. Slope equals height. I'm going to push forward 1/4 unit. That is my horizontal differential. So my vertical differential is what I'm trying to find. Slope is rise over run, which is 1. So dy over 1/4 is 1, dy is 1/4. That's my vertical push. So my new height for this point I've just plotted is 1 plus 1/4. Now I'll just do it again. I'm at my point 1/4, 1 plus 1/4. So my slope is my height, 1 plus 1/4, which is approximately the exponential of 1/4. Set up my differential, pushing forward a 4th unit. That's my horizontal differential, and my vertical differential. Rise over run is slope, and I'm going to solve for the rise. Fill in what my differential is. There's my vertical push. Push horizontally, I'm at 2/4. Push vertically, and I'm at a new height, the old height plus the dy. I'm at the old height plus the dy. 1 plus 1/4 is common, so if I make the first term a multiplied term, I can factor. 1 plus 1/4 factors. Leaving 1 plus 1/4. Same base, add powers. Do it again. I'm at the second step now. 1 plus 1/4 squared is my height. So that's my slope. Set up my differentials. Solve for dy. 1 plus 1/4, of course, is the exponential of 1/2, approximately. Fill in what my differential is in this case. And plot my new point. My new height is my old height plus dy. Multiply by 1 to have a common multiplied term that I can factor out. Same base, add power. Well, now the pattern seems kind of clear. We're doing the same thing over and over again, so I'll just do it again. I'm at 3/4. Height is the slope. Solve for the dy. The new height is the old height plus dy, same base at powers. And I'm at 1. Let's put down all the data that we've done, record all the steps that we've done. Here's all the points we've plotted. This function action, think of as happening to each coordinate. I'm adding in x and I'm multiplying in y. Adding in x, multiplying in y. Adding, multiplying. Successive multiplication, exponential growth. This is a key feature of exponential growth. So I'm adding in the input, and I'm multiplying in the output. Whenever you have this in any kind of data, this is exponential growth by definition. Now we're ready to do n times. We'll take n steps to get to 1, so each step is of size 1 over n. The bigger n is, the smaller the step size. I'll do my first step. Every time I'm adding in the input, I'm multiplying in the output. So I keep adding 1 over n's until I get to 1. So I've done n over n, I've added 1 over n times. So on the output side then, I'm going to multiply by 1 plus 1 over n times. Starting with x equals 0, I add 1. Starting with y equals 1, I multiply by 1 plus 1 over n to the n. So there's my approximation for the exponential function at 1. As n gets larger, 1 over n gets smaller. 1 over n is my h. So driving n to infinity is driving h to 0, and there's the definition of the exponential function of 1. This has a brand new symbol, e, that stands for it. This number is defined in terms of a limit. It's a transcendental number. Now that we go from 0 to 1, I can use this same function to go from 1 to 2. 1 plus 1 over n to the n goes in, and I multiply by 1 plus 1 over n to the n. Same base, add power. This is approximately then e times e, or e squared. Well, if it's good for 1 and 2, it's good for any number that you can get to. So for any x, it's 1 plus 1 over n to the xn. Multiply power, power of power, drive n to infinity, and the stuff inside the brackets goes to e. The exponential function at x is e to the x, and the derivative is itself. Because at every point, the slope, which is the derivative at x, is the height, which is e to the x.